Homework 15, Exponential Functions, Video 3. In the next two videos, we're going to explore the graphs of exponential functions, and then after that, we'll find more efficient ways to graph them. But we're going to do a couple of basic ones first, starting with f of x equals 2 to the x power. Now, if you have a graphing calculator, of course, you can put this in here and get the graph, but I'm not teaching you how to just press buttons. I'm teaching you to think and understand concepts. So I don't mind if you use a graphing calculator to support your work, but if you use your graphing calculator to replace your work, it can backfire on your test. Trust me, this is not my first rodeo. Well, we can always graph a function the old-fashioned way by just plugging in numbers and connecting points and seeing if we can make some observations. And then later, the more information we know, the less work we have to do. So let's attack this the old-fashioned way by just substituting some values into the function. I've already selected the values from 3 to -3, which are always a good set of values to start with. Sometimes you need more values, but I think these will do the job for us. If we substitute 3 into the function, we get 2 to the 3rd power, which is not 6. It's 2 times 2 times 2. 2 times 2 is 4, times another 2 is 8. As we start calculating the outputs, let's go ahead and start plotting some points. Over 3, up 8 is about here. So here's 3, 8. Not much to go on. Let's put in 2. And remember, the input is taking the place of the exponent. So we have 2 to the 2nd power, which is just 4. So over 2, up 4, it's about here. Oh, it's a line. Don't you ever draw a graph with 2 points, even if it's supposed to be a line. Because if you draw a graph of a line with 2 points and one of the points is wrong, you have no way of knowing. I need more evidence. Let's put in some more x's. Put in the 1 for the exponent, we get 2 to the 1st power, which is just 2. So our next point is 1, 2. Over 1, up 2. And my apologies, this is not the point 2, 2. This is the point 2, 4. Now, you may be thinking, sorry folks, you may be thinking, oh, it's a line, I think. But if you were to draw it accurately, you would see that these 3 points are just not quite collinear. We need more evidence. Let's put in 0. 2 to the 0 power equals, what is 2 to the 0 power? The casual observer will go, that's 0, because we're not multiplying any 2's. And the casual observer would be wrong. Because if I erase these problems and just asked you what number comes next in this pattern, 8, 4, 2, looks like the numbers are getting cut in half, and you would be correct. So actually 2 to the 0 power is 1. It's not just because I said it or because it completes the pattern, it's because there are some exponent rules which you may or may not remember from the past, but I'm pretty sure you have seen. And because we're dealing with exponential functions, we will be running into these exponential rules quite a bit. So as we run across them, I'm going to catalog them over here. One exponent rule is that if you raise anything to the 0 power, you get 1, except 0 to the 0 power. Try putting 0 to the 0 power in your calculator and it'll go error. If it's a really sophisticated calculator, it will say indeterminate, but that's a discussion for a calculus class. My point is anything at the 0 power is 1, and if you don't believe me, ask your calculator what 2 to the 0 power is. So any number except 0 raised to the 0 power is 1, which means this order pair is 0, 1, which means I have a point right here. In fact, that's my y-intercept. We'll label it up here. 0, 1. Looks like at some point we're going to cross the x-axis, so we'll locate the x-intercept in a moment. Well, let's continue evaluating the function. Okay, 2 to the -1 power. Your instinct might say -2, because 2 to the 1st power was 2, so 2 to the -1 power is -2. Except that's not how negative exponents work. If I were teaching a lesson on exponent rules and building them, we would build this rule, but assuming that this is review, I'm just going to tell you what it is. Not just x to the -1 power, but x to any negative power. Actually, let's think about it. by finishing this table, by continuing the pattern that I think we see here. As we're moving downward, these y values are getting cut in half. Half of 8 is 4, half of 4 is 2, half of 2 is 1, half of 1 is a half. Half of a half is, take half a pizza and cut it in half, you got 1/4 of the pizza. And cut it in half again. Sorry folks, I got about 7 soaks in the fire. Cut it in half again and you get 1/8. Which are all actually the correct answers, but there's something more powerful going on here, pun intended. We've seen the number 8 in this list already, it was up here. 2 to the third power is 8, but 2 to the negative third power is 1/8. And we've seen the number 4 in this list already, it was up here. 2 to the second power is 4, 2 to the negative second power is 1/4. And the same thing here. 2 to the first power is 2, 2 to the negative first power is 1/2, which seems to suggest that the way you evaluate a negative exponent is to take the reciprocal of the positive exponent's answer. In other words, 2 to the negative 3 is the same as 1/2 to the positive 3. And in general, x to a negative power is 1/x to the positive power. We still have the stipulation that x can't be 0. That would be bad in the denominator. So the way you evaluate a negative exponent is you don't. You evaluate the positive exponent and then you reciprocate the answer. So now we get the rest of our dots. -1, 1/2, which is back 1 and only up a half. So -1, 1/2 is there. -2 up a quarter, so it's up half as high as the previous one. -2, 1/4. And by the time we get to -3, it's only up 1/8. It's barely off the x-axis. So -3, 1/8. Sorry, I know it's hard to see these fractions. So what's going on here? We haven't hit the x-intercept. And guess what? We're never gonna. Because the pattern going from right to left is that these points are half as high as the previous one. So every time we move across 1 to the left, the point is half as high off the ground as it was previously, but it will never actually hit the ground. In other words, this graph, which is rising on the right, sorry I missed it, kind of bends, hits the y-axis right here, but as we cross the y-axis and start coming over here, we keep getting closer and closer to the x-axis, but we'll never cross it. Wait, we've seen that before. In the last series of videos, our functions had lines that they approached but never crossed, and they were called asymptotes. The x-axis here is serving as a horizontal asymptote, but just on the left side, so I guess that makes it a half asymptote. And then we have the graph of our function. So what can we say about this graph? Well, we can say several things. Number one, the y-intercept is 0, 1. That's because any number to the 0 power is 1. This graph is increasing, and what I mean by increasing is if you think this is a roller coaster going from left to right, you are always going up. This graph has no x-intercepts because this graph has a vertical asymptote at x equals 0, at y equals 0, the equation of the x-axis. Let's see, we can talk about domain and range. The domain is, well, this graph goes forever to the left, and it goes forever to the right, but it gets ridiculously high as it does. So the domain is -∞ to infinity. What about the range? Well, I know how high it gets. Insert your own Colorado joke there. But how low will it get? Because of the asymptote, it's going to get closer to 0 but never touch it. Which means this range starts at 0 with the parentheses, because again, it never touches the x-axis. Just keeps getting closer and closer and closer. So a lot of exponential functions will have graphs that look like this. They start out hugging the asymptote, hugging the x-axis, and then at some point it takes a sharp turn and goes upward. You hear everybody talking about exponential growth with the propagation of the COVID-19 virus. around the county, the state, the country, and the world. It's exponential growth. Well, this is kind of what they're talking about. That if left to run its natural course, the spread of a virus will start like this and then go like that. Now, when they talk about flattening the curve, that's actually a statistical concept, so it's not to be confused with that. But I'll be honest, the spread of coronavirus could not keep doing this because this goes up to infinity and the population is not infinity. Actually, what the spread of a disease would be when left unchecked is it would start out slow, it would skyrocket, and then it would start to plateau as you start reaching the population level. But that's assuming nobody recovers and nobody dies. So it's not entirely an accurate model. So all you people out there on Facebook throwing out math terms, please check your terms before you start talking about them again. In the next video, we're going to do another graph of a function that's going to look kind of the same, but a little bit different for a good reason.